Hello, and welcome to this WAGO tutorial where we'll guide you through configuring a server and client using the IEC61850 Telecontrol protocol. In the IEC61850 standard, data points are primarily created on the server and then transferred to the client. There are two methods for this: either export an SCL file with the data structure and import it into the client, or with some servers, the client can read the available data structure directly. We'll start by configuring the IEC61850 server. Begin by clicking the Server button to add it. First, ensure the IEC61850 server tab is selected in the right pane, where the possible models are provided. In the general settings, you can enter a comment and name the server. With the 61850 protocol, it's crucial to ensure names are consistent everywhere, as the client queries or writes data via the path names. The path name is derived from the data structure, branching out like a file or folder system. For the subnetwork, you can assign a name to this area in the SCL file, and network settings will be listed here. Exporting the SCL file and viewing it with an editor will show the subnetwork area with the network settings. The connection settings specify the server's network parameters so they can be transferred to the client with the SCL file. You can also set the network protocol, TCP or TLS, how often the connection to the remote terminal is checked, and a password. The default port is 102. Multiple clients can be specified in the server, each generating a separate report. Even if two clients receive the same report, select to here, as a report is only logged for one client. We'll discuss reports in more detail later. Additionally, you can specify a bool variable to indicate the status of the connection. Next, let's examine the structure of the data points. In the right pane, under Models, initially, only the logical device item is visible. Adding this to the server using the green plus sign shows that logical nodes LLN0 and LPHD are already attached, with some items already created. This includes data objects and the reports folder in LLN0. The general procedure is to add a required logical node from the model window on the right and fill it with data objects. LNs and DOs are labeled and structured differently depending on the industry. For example, in the wind turbine folder, you'll find the logical node WGen for generator values. Adding this will include the general data object, behavior, and the data object rod speed, which provides the rotor speed as an analog value, along with quality information and a timestamp. The logical node WMET for metrological data contains only the behavior data object. For example, if we want to analyze the wind speed, we need to attach the wind speed data object to WMET. In the list of possible data objects, we find two for this purpose: the horizontal wind speed and the vertical wind speed. Since in most cases there is only one sensor for the horizontal wind speed, we select the horizontal wind speed data object. This process demonstrates how the data structure builds from the logical device, LD, to several logical nodes, LNs, each with multiple data objects, DOs, and various data attributes, DAs, showing how extensive and industry-specific the IEC61850 protocol can be. To keep things simple, we'll use the generic logical node to show the basics of the IEC61850 protocol and how to configure a server and client. The LNGGIO is commonly used in WAGO solutions to convert signals from Modbus to IEC61850 Telecontrol. First, delete the wind turbine and add the LNGGIO to the project. Initially, it only contains the DO behavior, so add an alarm, an integer value and a DO for a single point command. For alarm 1, the typical structure includes the variable, quality information and timestamp. With options for entering comments, actual variables, and setting the trigger for when the alarm is sent to the client. The IEC61850 protocol allows the client to request individual data objects. If the server reports a change in a variable's value to the client, this is done via reports. Now that we are creating a report block, we can select a data set at this point. As we have not yet created a dataset, the drop-down menu is still empty, so we create a dataset. When we select this, our previously created data points appear in the right-hand model window. Under GGIO1, we find the alarm and the integer value, which we add together with the quality information and the timestamp. We do not add the single command SPCS01 as we receive it and do not report it. The dataset is now created and we can access it in report block 1. Here we also find the various trigger options. If we only want the report to be sent when the value changes, we leave the tick next to data change. In summary, create data points, combine them into a dataset and send the dataset as a report. Back in the alarm1 data object, we create a variable. The trigger option is already set to data change. The initialization value is also set to false. With the tick, we could initialize the variable with true. If we look at the data quality, the trigger option is already set to quality change. We also assign a variable here. This then contains the quality information as a bit string, which is then coded as shown in this table. The first 2 bits indicate the validity status: good, invalid, reserved or questionable, followed by further quality information such as buffer overflow or marking as test. We can also enter a comment and a trigger option for the timestamp. In the same way, we now assign the variables and so on for the integer value and the single command. To go deeper into the reports, we create a new report block and reassign dataset 1 to it. This should only be sent when the quality status changes. So we just tick the quality change box. The integrity period allows cyclic report sending, for instance, every 1000 milliseconds, regardless of changes. A change in the quality string occurs if the time on the server has not been synchronized for a certain period of time. Then the timestamp is marked as invalid. When such an event occurs, it affects all data objects, which all trigger a report. The buffer time can be increased to accumulate such events. All triggered events that occur within the specified time will then be sent in a single report. It is also possible to select whether the report should be saved if the remote station is not available, so that it can be sent as soon as communication is active again. In the IEC61850 protocol, a client must actively reserve a report for itself. We selected 2 clients at the beginning, and when we go back to the report, the configurator has been updated and only 2 client addresses can be specified for reservation. The Telecontrol stack will then create 2 identical reports in the background, each reserved for 1 client. We leave the general options at the default settings and have now created 2 reports. The first report is sent immediately when the value of a variable changes, and the second summarizes changes in the quality string over 500 milliseconds. This means that a wide range of reports can be created from the data objects, which then provide precisely defined content. Other examples would be all active powers every 10 minutes or all door contacts when the value changes, and so on. Let's look at the command. If we expand the structure, we see the status DAs with the abbreviation ST and the data attribute SPC operate with the abbreviation CO for command. This is the actual value described by the client. Expanding on this, we see a number of additional attributes, such as timestamps and so on. The actual variable that is then mapped to the digital output to switch something is the data attribute CO boolean ctval. Commands often require a response from the field level to confirm that the command has been executed. This feedback, for example, a signaling contact of a circuit breaker, is then mapped to the status data attribute st boolean stval. The way in which the command is executed, directly or pre-selected, can be selected in the CFCTL model data attribute. If the status only option is selected, the command is not executed. Only the status is queried. And then the two options, direct execution and SBO for select before operate. Both options can also be run with enhanced security. Here we select direct execution with basic security. This completes the configuration of the server for our example, and we can load the project into the controller and start it. After logging out, we want to create the file that we will transfer to the client. To do this, we click on Export and can select different file extensions. Save the file and launch the client. The structure. Now we have a PFC running as a server. We want to operate another PFC on the same network as a client. To do this, we connect another controller, add the Telecontrol configurator, and start the configuration. First, select the Client tab and add it by clicking on the Client button. In the right model window, we switch to the Client tab and can either browse the server, that is to read it out via the network connection, or open the previously saved SCL file. We browse the server. The server is displayed with the tree and we confirm with OK. The server tree is now displayed in the right pane in the IEC61850 Client Model tab. First, we add the server by clicking on the small plus symbol. This is still empty. If we now open the server tree, we can add a dataset. The Telecontrol configurator then pulls in all the associated data so that we now find the GGIOs of the dataset in the data points. If we compare this, the single alarm and the integer value have been transferred, but not the switchable status output SPCSO, as this is not contained in dataset 1. To be able to use the data points in the application, we need to create variables. To do this, we go to the data attributes and can then assign variables to them. The same applies to the quality information and the timestamps. There are two ways of requesting the dataset from the server. We can either poll the dataset cyclically, for which we set a cycle time here, or we can trigger a request via a variable. As a first test, we log into both controllers and start them. In the server's global variable list, we write a value to the analog value variable. After 20 seconds, the client polls the dataset and the value is now also displayed in the client variable. And polling the dataset via the trigger variable also works. Now we want to set up the reports on the client. First, we add them with the green plus sign to receive a report it must be activated by the client and is then reserved exclusively for that client. On the server, we have specified that 2 clients will have access, which means that 2 reports will be created. In the instance, we can then specify whether the first free report is automatically activated or, for example, always the second report is reserved for this client. Activation can take place automatically with activating the link, or it can be triggered manually by a variable. For a better demonstration of the function, we will select manual activation and assign a variable. With read trigger variable, we can request the report from the client side, and with the tick in general query, it will also be sent in a general query. The same settings as on the server side, such as buffer time or trigger options, can be found below, so we can change these settings again from the client side. If we now log in into both controllers, we can see that a status change for Alarm 1 is not being transmitted because we have not yet activated the report. The status change will only be transmitted immediately when the report is active. Commands. The control function is available for commands that we select in the client window. We can find the command created in the server, SPCSO, in the model window, and add it with the green plus. The command has been transferred to the client and we can open the settings window. In this section, you can specify when the command is to be executed, automatically when the value changes, which is often used in gateway applications, or manually triggered by a variable. At the top is the comment and the structure, which must be the same in the client and the server. Then the control model is selected. With enhanced security, command execution errors are reported to the client. We leave the originator category, originator identification, and check condition at their default values. And for the data point, we enter the actual bool variable. Translate, log in, and start on both controllers, of course. And we can test our program. If we now set the XCMD1 client variable to true, it will be transferred to the server and the corresponding variable will be set to true. Of course, for a real application, the timestamps, quality bits, and feedback from the field level would still need to be created, but for the purposes of this example, we will leave it at that. We will go into more detail about timestamps and quality bits in the video on gateway applications in Telecontrol. A special feature of IEC61850 is the Goose protocol. The Goose protocol is used in particular for protection devices to send fast and reliable messages, operating at OSI level 2. That is the MAC level. The Goose protocol ensures messages are received by sending them multiple times with increasing intervals. The Goose control block is a separate area of the server for the Goose protocol. It also works with datasets, so we can select the previously created dataset here. Here is the possibility to define version states or to simulate a transmission with test telegrams. Then we find the minimum and maximum repetition time for sending the message. In this case, the message would be sent again 500 milliseconds after the first message, then again after 1 second, then again after 2 seconds, then 4 seconds, and finally after 8 seconds. This ensures that the subscriber, in this case the client, receives the message. As communication runs at MAC level, we only need to enter the MAC addresses here. We can search for the source MAC address. In the case of the PFC, it is bridge 0. The destination MAC address is initially a default value. If we leave it as it is, all participants of the Goose protocol can receive the telegram. Alternatively, a single MAC address can be specified here. As we are not using a virtual LAN, we leave the VLAN option unchecked. The Goose protocol is already configured on the server side and we export the settings as an SCL file. We then transfer it to the controller and run it. On the client side, we theoretically do not need a client. We delete it and add the IEC61850 subscriber instead. However, it is possible to run the client and the subscriber in parallel. Since something has changed in the server, we need to open the SCL file and find the previously created Goose block 1 in the server structure and import it. We find the data attributes of the dataset and we assign variables for the analog value and alarm 1. In the Goose block settings, we can see that almost all the data has already been transferred from the server. Here you can set the options flags, once if the telegram was sent as a test telegram or if a telegram is expected within a certain time but does not receive. It's called the time allowed live flag, and a variable can be set. The variable behavior can be set here. For the test, we transfer the program to the controller, start it, and if we now set alarm 1 to true in the server, it will also be true in the subscriber. The same applies to the analog value. The only difference is that the telegrams are no longer sent via IP addresses, but directly at MAC level. This concludes the IEC61850 Telecontrol protocol tutorial, providing an initial overview of this powerful protocol. Of course, there are many things that we have only touched on very briefly or not at all in this tutorial, but often it's so industry or application specific that an individual advice from our support team is more appropriate. Please give us a thumbs up and subscribe to the channel so you don't miss the next Telecontrol video on gateway applications.